Okay, so the final part of chapter 4 then is to look at what happens when we apply some small perturbations to the lateral directional forces and moments. So the first part of this follows pretty much exactly the same process as we saw in chapter 3, where we applied small perturbations to the lift and drag forces and the pitch moment. So the first thing to consider is what variables affect our side force and also our roll and yaw moments. So in the lateral sense, we have these variables which all affect the side force, the roll moment and the yaw moment. So side slip, velocity in the y direction, roll rate, yaw rate, and angle of deflection of both the aileron angle and the rudder. Also, we have to consider the rate of change of side slip angle too. So what happens is we assume that small perturbations in our forces and moments are essentially small functions of small perturbations of all of those variables, right? This is what we saw before. And then, as always, we can apply a Taylor series expansion to each of these three things here to get this system, where this has been evaluated at the steady state condition again. But again, we end up with a system of equations that is dimensional. So if we want to non-dimensionalize that system, we have to make the following substitutions, which again are similar to the ones that we made in the previous chapter. Then we get this system, which looks even more of a mess. And then to tidy this up a little bit, we can write some of these partial derivatives as lateral force, roll moment, and yaw moment coefficients to get this, which is a little bit neater, right? So this system of equations now contains 18 coefficients, okay? But the good news is that nine of them have been derived previously, these ones here. The other 9 we now have to deal with separately. So here we go then. So starting with the coefficients of lateral force, roll moment and yaw moment due to small perturbations in the rate of change of side slip. Bit of a mouthful, but essentially we can consider all of these as negligible because our side wash effect is, as we said earlier in the chapter, much smaller than the associated downwash effects. So like when we saw all of the alpha dot terms in the previous chapter, those terms are more significant than these ones, so therefore we can assume these beta dot terms are negligible. So then let's move on to look at the lateral force coefficient due to roll rate. Reasonably intuitive that the main contributor to this coefficient is the vertical tail, so that's the only one that we can consider, and therefore we can consider the moment as again a force that's been previously derived multiplied by the associated moment arm. The next one is a particularly interesting and important one. It's the roll moment coefficient due to roll rate. This is otherwise known as the roll damping derivative, because if you consider my little sketch over here, this is an aircraft aft looking forward, so we've got a positive roll rate, so right wing down. In this situation, the right hand wing, or the down going wing, sees essentially a higher angle of attack, so produces more lift than the up going wing, which acts to counteract the roll moment, right? So that's why it's called the roll damping derivative, because the aerodynamics of the wings produces an opposing roll moment to this one. So how do we mathematically model that? Well, again, we split this up into terms associated with the wing and body, horizontal tail and vertical tail, and deal with them separately. A couple of things to point out here: the coefficient associated with the wing and body combined depends on this thing called RDP, the roll damping parameter. Again, that's just another thing that you can look up on charts based on some basic dimensions and other parameters like the Mach number and the side slip angle. Then there's a coefficient associated with the horizontal tail. Very often this is 0 because we have these ratios of the reference area and span of the horizontal tail ratioed with respect to the main wing. So obviously those values are going to be very small typically, so often we can assume this one is 0. And then finally, the one associated with the vertical tail is based on a coefficient that we've already derived and a moment arm. So next, let's consider the yaw moment coefficient due to roll rate. Again, we split that up into coefficients associated with the wing, body, horizontal tail, and vertical tail separately. The contributions from the wing and horizontal tail can be considered negligible, so that leaves the contribution from the body and the vertical tail to be considered separately. Again, all of this stuff goes into an equation which is based on some previously derived coefficients. Remember that epsilon sub w is the wing twist, so there's a coefficient associated with that. And again, a lot of these terms can be looked up in the various figures in the textbook based on some basic properties of the aircraft. One other assumption that's been made in cancelling out these two terms is that the small angle approximations that we've seen in the perturbation sections previously is that the sine of a small angle is the small angle in radians, and the cosine of a small angle is 1. So if alpha 1 is small, then we can approximate these tan terms as 0, which is why I've cancelled them out here. And again, the vertical tail component is again a previously derived coefficient based on lateral force multiplied by a moment arm. Next, let's look at the lateral force coefficient due to yaw rate. Again, we only need to consider the vertical tail here, as that's the only significant contributor to this particular coefficient. Again, this is just based on a coefficient that we've previously derived based on the side slip angle and a moment arm. And you can see that this one is very similar to the CYP coefficient, this one up here. The only difference is the moment arm associated with that force. Okay, we're nearly there then. So the second to last one is the roll moment coefficient due to yaw rate. Now again, this is a particularly important one. So what happens, so essentially what we're describing here is adverse roll. So if we have a positive yaw rate, so the aircraft is yawing nose to the right about the center of gravity position, we have essentially one wing that's advancing or is essentially moving faster through the air than the retreating one because it's rotating in this direction, and because this one therefore produces more lift than this one, then you get a roll moment associated with that yawing as well. So what we're describing there is adverse roll. So again, we split this coefficient into 3 parts. The horizontal tail we again assume is going to be negligible, and again we consider all of these parts, some that are due to the wing dihedral, some that are due to the wing twist. We take this equation and we essentially convert it by evaluating it at Mach equals 0 and introducing this constant, which we can look up from the tables and charts in the textbook. One thing I wanted to point out though is this special kind of figure, 4.85 from the textbook. So let's have a quick look at that and how you read it. So here we are. Ignore the mistake in the textbook, but essentially what we do is we work out or we find the aspect ratio, the taper ratio, and the leading edge sweep angle at a quarter chord, or the sweep angle of the wing at a quarter chord, and then we read around the chart in a circular fashion. So we start down here, look, with an aspect ratio. We find where's the most similar aspect ratio to our aircraft. We read up until we find the most similar taper ratio. Then we read across to find the most similar quarter chord sweep angle, and then finally read all the way down to find a value for this thing. So it's a little bit like choose your adventure here, right? So just based on a few different parameters, you can read around this chart, find a little bit of a puzzle, right? So that will give you a value for that then you can go ahead and stick into there. So again, a lot more eyeballing from charts and reading of graphs and that kind of thing. And then finally, the coefficient associated with the vertical tail, again, previously derived coefficient and a moment arm. So that leads us to our final coefficient and the final part of chapter 4, which is the yaw moment coefficient due to yaw rate. Again, we split it up. Horizontal tail component is 0, and then we have coefficients again, which we look up from the charts. Now we've reintroduced these parasitic drag coefficients, which we derived in chapter 3, I guess. The other components we can look up from the charts, and again, the vertical tail component is based on this previously derived coefficient and an associated moment arm. So there we go. Hope you followed all of that.